All right, welcome to the workshop. I've been getting everything set up. Got some interesting measurements. So let me go through the setup here real quick. I've got an oscilloscope with two channels here. Two channels are leading to the two what seem to be signal wires on the remote. The remote's wired into the winch on the inside of the Forerunner. So this is an oscilloscope. You can kind of imagine it like a multimeter that measures voltage over time, then displays the voltage on the y-axis and time on the x-axis. What I'm seeing here is kind of a pattern of long, short, short, short. This is for spooling out, and then on spooling in, it was short, short, long, short. I think it's probably safety related. You can imagine if one of the signal wires gets shorted to power with traditional winches, that could cause the drum to start spooling uncontrollably. Whereas this, if you've got some kind of a signal, a short isn't going to turn on the winch. Unfortunately for us, that means that we've got to have something smart that can send out these pulses, and we can't just, flip a switch. And maybe you saw the blue line on the oscilloscope where it kind of droops and fades slowly over time. I don't even know if the blue line is used, so I'm going to try disconnecting it and see if the remote can still control the winch. Yeah, so it seems like the winch will run without it. Warren, got any engineers who want to let me know what decisions led to this regime? So what we've established is there's some kind of smart brain on the controller side that creates these digital pulses that get sent out and interpreted by some kind of brain on the winch side that then controls the motors. We've also determined that one of these signal lines isn't used. Finally, we're still trying to figure out how these switches interface with the brain, so we're going to keep digging. I think I'm going to use this brain for a brain transplant for our in-cab controls. Now I'm going to use my multimeter. I've got it in conductivity mode, so whenever there's good conductivity between the two probes. So I'm just looking at these switches and trying to figure out, do they conduct across horizontally? So now when we push the button, it should beep. Might be a little bit tough to see here, but there are 4 pads on the switch, and so these top 2 are the same node and the bottom 2 are the same signals. And then when you push the button connects the top to the bottom. And then for this measurement, I want to measure what's actually going across the switch. So let's take a look. So this is the lower pad on the switch, and it seems to have a pull-up resistor, and then when you push the button, it grounds it. So you can see on the screen back there maybe. I'm going to push the button and the signal drops. And then same kind of story on the bottom switch. It's being pulled high normally, close the switch, and it gets pulled down. So I wanted to do a little visualization of what I was talking about with the pull-up resistor. That might be kind of an odd term for a lot of folks out there. This might be what you would expect for a button that closes a switch and then switches the input from low to high. This is kind of like if you have a light switch wired in your house, it just opens and closes a circuit. We don't use this as much in like embedded electronics. It's like if you close this switch and then open it again, the charge can just stay on this input. There's nowhere for the charge to go. So what we usually do is this scheme over here where you've got a resistor pulling up the input normally, and then when you hit the button, it will connect the input to ground. This prevents the case where you've got a floating input, and then it's also nice if you have one chip talking to another chip and the 2 chips are on different voltages, that it's just easy to get the right input drive voltage by using a pull-up. This is the switch that I've got for the winch. On the bag for this, green and orange are clearly the outputs, and red is labeled as 12 volts plus, but really the red is just the input for the switch. Whatever you want put on those outputs, you put on the red. The switch is just connecting red and green and orange on the inside. I've got my wires hooked up to green and red right there. Green should be out. So when we push out, we get conductivity. All right, then just to prove it, orange should be in. There we go. For our design where we want to pull down the pin, we're going to connect what's labeled as 12 volt on here, the red wire, to ground. So for this little proof of concept here, we're going to solder the wires directly to the same pads that the switches are already hooked to. Here are our original switches that were on the controller brain board, and we've got our little pull-up resistors represented here. So when you close the switch, the inputs would get pulled down. So what we're doing is we're going to piggyback these switches on the toggle straight onto these solder pads, so that instead of pressing these on-board buttons, we can use our toggle switches to pull that input down to ground. Let's do this other guy. Soldering's done. I'm going to plug in our winch connection so we know that these buttons work. And we have our switches, the outputs connected to pulling down the inputs, and then our input is the system ground. So, proof of concept works. I'm not in love with how thick these wires are connecting to little teeny tiny pads. I'm going to try working up like a little 3D printed enclosure for this thing that can have a little connector going into that's more robust and is going to last 30 years, not 30 minutes. Catted up this little representation of the PCB. This guy, that's coming from inside the controller. Now we can build an enclosure around it. All right, now we got a little box enclosure. Now we can make a lid. And here's a shot of our lid. I drilled some holes so we can see the LEDs. I'll try to print this up. Yep, looks like this one turned out. There's our little enclosure. And it feels pretty cool to have a little custom enclosure. I mean, look at that. I just inserted that little JST connector with these leads on it, and it's a press fit. Like, I don't think I even need to glue it in there. These will be our in and out signals from the switch. Here's the signals that will go to the winch. We're doing some final checks here before we start installation. We've got our little brain box. LED cutout is working perfectly. And then we're hooked up to the worn cable again and go into the winch. And then we've got our wires hooked up to the switch. The last thing that I want to do is take some epoxy and really secure these wires in. Say goodbye to the board. This will be the last time that we can see it. Sealing it up for all eternity. It's like King Tut's tomb. I'm starting to wire up the switch inside the cab. One decision that I made was that I wanted to put the switch on the ignition 12 volt. That way if the key's not in the car, the winch won't operate. These are my existing switch connections, and you can see the brain in here that we built. And I was just going to do a quick sanity check turning on the 12 volt ignition. So there's our red LED lighting up. So far so good. There's little diodes on that switch that light up when the switch is in the on position. The diodes were providing a path to ground that wasn't there before. I'm not going to use the ground, and I'm not going to have those LEDs that light up, but everything should work. I don't know if you can see the oscilloscope in the background. We have signal. Back around the front of the truck, I took that worn winch cable that used to have the 4 wires, and all we're using out of there is that white wire anymore. A little spade connector on there, and I had already run a spare wire through the firewall. So we're going to plug that up. We should be able to control the winch. It worked! So that's a wrap on that project. Let me know if you have any questions.